Hello, everybody. Welcome to the first ICE Lab seminar. We hadn't had any almost for a year, so it's really nice to resume these talks. And this year, our first guest is Pavel Sulimov. He's from Switzerland. He used to be my former PhD student, but now he's like a rising star in academic research. And now he's in Switzerland. And he is going to talk about quantum machine learning, which is a very interesting field. And well, let's see what he says about it. Okay, Pavel, will you please start your talk?
Yeah. Thank you, Attila. Okay, I think there were a lot of big words, but yeah, some of them are true. At least that I was a PhD student by Attila. So basically, the topic is quantum machine learning, and what I want to make like a disclaimer. I would try to be with you as frank as possible because exactly, the topic is very hot, very sexy. But let's be honest, not all the things that are claimed are working, and yeah, this is far away from where people consider it to be, who are selling it. So today I'm going to try to sell it to you, but without a fancy wrapping. So, still, for those of you who do not have kind of the background in quantum technologies and quantum physics, you
basically, what it would look like is the data itself, and this is
Can you mute
data
him?
from.
I thought there was already a question coming. Okay, yes. So, but literally the thing is that you definitely know like classical bits that are in the classical computers, that everything is encoded like 0101. But let's say the quantum bits, what we like call qubits, they're a little bit more fancy. So basically, this is just, let's say, rather the mathematical function, but not just the simple 0, 1. And the thing is that with this function, we're just providing the probability of our bit being 0 or 1, and we only find out if it is literally 0 or 1 after measuring it. So there is like in quantum physics the procedure of measuring. So basically imagine that you have a ball that is rolling, and then at some point you are saying stop, and it's gonna occur either on the side with the 0 or on the side with the 1. And only thing you are controlling is exactly this probability towards which part the ball is shifted. If it is like shifted towards 0 or towards 1, but obviously there is always non-zero probability, almost always non-zero probability that it's gonna become, let's say, 1, even if you say that it's 99.9 being 0. So, if you want to, let's say, look how it is, as I said, it's more a mathematical function. And, oh, yes, Attila, please. Unmute.
Can you go back to the previous slides?
Yeah, sure, absolutely. Just let us go back to the previous slide.
Okay, so first of all, the quantum bits a little bit hurts my eyes. Why do they use this unpaired parentheses?
So you just okay. So this is just the notation. This is called bra and cat notation. So bracket notation. Basically, I am clarifying it on the next slide. Sorry, here I just provided it like this. Yeah. If this was the main question, let me clarify it here. So literally here I'm a little bit unfolding it, saying that this 0 it means 1, 0, and 1 it is 0, 1, and basically these are kind of the probabilities, or to be more precise, these are not probabilities, these are amplitudes which are proportional to probabilities. Because what you can see here, for example, if I have, let's say, my quantum bit in this state, it is called state. Basically it means that when I'm gonna square these things and sum them up, they're gonna occur to be 1. The reason why we do not call them explicitly probabilities is because they can be negative, they can be complex valued numbers. So basically they are proportional to probabilities. Yeah, and let's say, as I said, yeah, you are providing, let's say, your shift towards 0 or towards 1, but since it is like a 3D and it is called Bloch sphere, this sphere where we are representing our quantum numbers, basically, yeah, you can, let's say, rotate here, and finally, when you measure, the probability is going to be the same, but it matters just for other things. So basically here you are saying that probability of measuring 0 equals to 1, and probability of measuring 1 equals to 0. Yeah, here it's vice versa. Yeah, so 0, 1, 1, 0, a little bit sophisticated. But if you then look now at this sphere, you would understand that the main thing that we can do with our qubit, quantum bit, is rotating it. So basically, let's say this is our bit, and what we're going to be doing, it's going to always stay on this unit sphere, but basically we're going to rotate it here and there in order to make it closer to 0 or closer to 1 pole. Yeah, so here are 2 poles. Is it more clear now, Attila, in terms of notation?
So do we have a probability distribution over this on the top of this unit sphere?
So this is kind of the thing that, yeah, so basically, since it is unit sphere, basically in every part, you have representation in terms of these coordinates. So basically you have like coordinates in, let's say if you imagine that here, we can represent xy as the complex number, and then for example, zy as another complex number. Then basically you're going to have always a value that is represented by these 2 complex coordinates. Yeah, and finally, you always gonna have like the only, let's say, probability distribution that we can describe is that the sum of the squares of these 2 coordinates is always 1. Other than that, we do not have other specific properties.
So is this a good thing for us, or it's a bad thing?
It's a good thing for us because it makes things much easier, and I'm gonna later explain you why. Yeah, so basically this is pretty good. So it means that we have, let's say, this kind of representation, which then we can use. And yeah, as I said, like maybe let me go a little bit further, and I'm gonna tell you why it makes sense. Yeah. So, and let's say before we come to this topic of quantum machine learning, I'm pretty sure that definitely you have heard something about quantum in terms of encryption and decryption. And I mean, for example, you definitely know that, for example, your emails, they are encrypted. Yeah. So when you are sending an email, and for example, one of the ways how you can encode it, this is very well-known RSA algorithm, which is like slightly discussed here in the bottom left corner, and the main idea is that it just stays like a huge theory behind the our naive assumption that if there are prime numbers p and q, and we just know their multiplication, the result of their multiplication, if these p and q are big enough, we would almost, let's say, never guess what were these p and q originally. So literally factorization of the huge number that is the result of multiplication of primes, there are not that many methods how you can do it rather than just with brute forcing. So yeah, literally when the number is huge, you just, the only thing that you can do is brute force it in classical way, in our understanding, yeah, of numbers. And to show like how huge this number could be, for example, 21st of October 2024, so last year in the end, there was like another Mersenne prime number like revealed. So Mersenne prime number is basically you have like 2 power p minus 1, and it occurred that this one is prime. And you can imagine that if I use, for example, this number, huge number, and even, I don't know, multiplied by whatever, 3, you still would most likely like be guessing like trying to calculate forever this one. And as I said, classically, it's very hard to find this out. But there is a guy who is called Shor, and I'm pretty sure he's still alive. And at some point, he has introduced such a called Shor's algorithm that says that, okay, yes, it is like the only way to find out these, let's say, 2 prime numbers is guessing. But what if I tell you that in quantum, let's say, in quantum world, we can have like, let's say, educated guesses. And if you are making, let's say, just the guess that is not true, so you're making this guess, for example, you're saying 9, it says no, you checked it, it occurs that 9 doesn't suit. We are saying that 9 power, somebody's throwing. Okay, I see a little bit of mess, but no problem. So, and it occurs that we can have like a little better guess, so just because of some mathematical theory. And yeah, unfortunately, in order to solve this stuff, we would need to know something that is called quantum Fourier transform. But for curious listeners, I have here added these 2 YouTube links to the guy who is explaining the idea behind this. But what I can tell you is that why here, let's say, quantum think makes sense, yeah? Why this non-deterministic, let's say, understanding of digits makes sense. Basically because quantum, and you might hear it from people, that quantum means that we can solve all the problems at once. So it means that, so you might hear this stuff that qubits could be at all the positions at the same time. Yes, so it is like 0 and 1 at the same time. And if I add another qubit, it's gonna be that we can have like 4 outcomes, 0, 0, 0, 1, 1, 0, 1, 1. And meanwhile, we didn't measure it. They all are possible. Yeah. And basically, that's why, some people are saying that with this, if we introduce something, if we encode something in quantum, we just can have all the possible solutions at the same time. And we just need to choose the best one. The reality is that, yes, if we have some, let's say, quantum bit encoding, we somehow encode the problem. It means that we have all these outcomes like 0, 0, 1, 0, 0, 1, and 1, 1 at the same time, but we have just the probabilities of them. So basically what quantum algorithms do, if you encode some problem in a quantum way, so that you are saying that this is like 0, 0, whatever, like 4 qubits, for example, basically you can measure at the same time, parallelly, all the probabilities of your outcomes, yeah? But it doesn't mean that you're gonna let's say, obligatory get the right solution, yeah? For that, you just need to somehow, let's say, so basically now, what is the idea here behind? That you are encoding your numbers, yeah, that you encounter here in the not in classical bits, but in this kind of bits, and then you are searching for the solution via the amplification of probabilities. So basically you are doing iterations and you are trying to increase the probabilities of the good answers, yeah? So, and that's why we're going to talk with machine learning, that it's good that you know in advance the right answers, yeah, during training. So imagine that you can amplify probabilities of right answers, and vice versa, you can put down the probabilities of wrong answers. And this is how it's going to look like if you're going to open, let's say, quantum programs. You're going to see that this is like quantum bit 0, 1, 2, 3, etc. And these are then operations that you are doing on them. Yeah. So as I said, that majority of these operations are just rotating them. So you are somehow rotating these quantum bits with, let's say, initial state of being exactly between 0 and 1. And you are trying to make it such a way that you are getting the probability of the good outcome maximized, and vice versa. So kind of the maximum likelihood method, yeah, to some extent. You can say that this is what happens. You're basically trying to maximize the likelihood of the good outcomes having high probability. But even if you search on the internet, I mean, this picture I have taken from this Quantum Computing Stack Exchange, so people are trying to understand why exactly these kind of manipulations are done in order to get this quantum Fourier transform on the Shor's algorithm. So yeah, unfortunately, this is the topic of a separate lecture, but just for you to see that exactly the way how to make these amplifications of probabilities, yeah, and vice versa. This is exactly the skill that you should have here, and this is what we would try to learn. Yeah, so exactly like how to do it. And when people are talking about this, let's say, quantum advantage, yeah, looking at this kind of encoding of the problem and saying that now we're gonna make this amplification of probabilities, the idea is that since you can let's say, have them all in parallel, it occurs that at some problems, for example, Shor's algorithm, that it can solve this problem of factorization of the numbers in the logarithmic time, basically. So it means that you just, instead of just brute forcing and making it like enormously hard, you can significantly reduce the time. So that's why like quantum advantage means usually the speed up because of this efficiency of quantum algorithm with exactly parallel calculation of the probability. But the reality is such that, for example, for this Shor's algorithm, here, and even let's say for this number, if you look at it, that in order to be able to solve, let's say, this problem for the RSA encryptions that are used now, you would need at least 6,000 quantum bits. So in order to encode like really big numbers, and in order to try out to find out really big numbers, you need roughly 2 to the power 6,000, which implies 6,000 qubits. What you might imagine is that, and I'm just gonna maybe give you a little secret about it, that nowadays the biggest quantum computer, it has roughly 400 or 500 quantum bits. So, I mean, we're so much far away from exactly, let's say, making this work on the real world problems, and let's say apply to this exact Shor's algorithm. That's why at this picture, we are saying that we are getting ready for quantum in order then to get quantum advantage. So we are now, let's say, developing better and better quantum algorithms and trying to, let's say, reduce the number of quantum bits that are required in order to solve it more efficient, in a more efficient way comparing to the classical one, but the reality is that we are not yet there. So you're seeing today is here. However, I can tell you that if we make, let's say, one step back and say that we would talk not about, let's say, these quantum bits, but just, let's say, complex numbers. Why complex numbers themselves already is a good idea. There is a good example on this COSNET. This is, I mean, it was like a big hype, I think, like about a year and a half or 2 years ago. So it was like a hybrid complex valued neural network. And complex values in neural networks, this is not a novel idea, but these guys, they have found out exactly the way how to make them work efficiently. And basically, this was about images processing, saying that, come on, look, that images, that still, I mean, even now, even nowadays, this is going to be some, let's say, diffusion, transformer, whatever state of the art, but behind it, it's going to be still the architecture of convolutional neural networks. Either way, like, I mean, for images, we still continue using convolutions. And the problem with convolutions is that in the initial phases, when you're trying to extract the low-level features, these steps, they are pretty computationally costly. So, I mean, later on, you're already extracting these, let's say, so you're first extracting the low-level features, and later on, you're already coming to the features like edges, curves, ridges, and etc., etc. But what if we're gonna, let's say, make such a image representation that these shapes like curves, ridges, and let's say bulbs, they're gonna be immediately, almost immediately extracted without the need for this deep architecture. And these guys, they had really success about it. So obviously they didn't work like on super high resolution images, but still with applying this idea of quantum like image processing. So basically it occurs that with these sorry, quantum, not quantum, but complex numbers, using complex numbers, it occurs that it is pretty easy to extract these edges simply because like this complex number architecture, it works, like the black box. So you're making the, let's say, representation of kind of the wave. So you're kind of treating this whole as a wave. And with complex numbers, I mean, if there is like such a thing that is called Fourier transformation, and like having the Fourier transformation over it basically gives you a stable solution. So, I mean, again, you can go into this article to see it better, but basically this is all about this, let's say, natural stuff of treating, let's say, waves with the Fourier transforms and later then processing it already classically. But this is only about complex numbers, yeah? So here we make one step back and say the complex numbers themselves, they are more powerful since we have more degrees of freedom. So basically we operate with more degrees of freedom, and let's say if we now proceed to quantum, we would see that we have kind of already whole block sphere, yeah? So we already would be working in 3D. Meanwhile, in our normal case, we are working in kind of 1D. Your neuron is a 1D stuff, yeah? So, but quantum bit, yeah, or quantum neuron, this is going to be already 3D. So basically you can have much more degrees of freedom. Though in reality, I can tell you that people never do, like, let's say, fully this complex number or quantum solution, because in the example of this article before, guys only took the initial part using complex numbers in order to have like more efficient encoding. And then later on, they trained it in the normal manner. So what is usually done with quantum is even worse to some extent. You are taking the classical encoding, so you are classically starting processing your data. Then at some point, you are introducing the quantum intermediate part, which is looking like this one, yeah? So you already know it. So here are some rotations, like, and these are like quantum wires, yeah? So these are quantum bits. And later on, at some point, you are coming back to the classical circuits in order then to make some kind of measurement. Why you do this? This part you do because, as I said, the number of quantum bits is not that huge. So literally, for example, if you have, I mean, except from pictures, yeah? Pictures we're going to touch separately, but if you imagine, for example, I don't know, text, working with texts, yeah? So for example, you have like this huge embedding, yeah? You need to somehow put it into this circuit. Usually what you do, you classically make the dimensionality reduction. Then you are processing it with already the quantum circuit, and it's called circuit, yeah, that has, let's say, the smaller number of bits. And let's say if you would like to do it on your just PC that you have at home, most likely you would not be able to simulate it. Yeah, so this process we can simulate without quantum computer, but let's say 32 bits, this is going to be the maximum. So it means that you can have 32 entries. So even if you have a strong GPU. Otherwise, it's going to be impossible. And then let's say having these 32 wires, you're finally coming back to some task, because basically you already might have mentioned that what we get in the end are the results like here, 0, 1, let's say 0, 0, 1. So if your task, for example, is regression, you cannot get, let's say, the real number, yeah, as the outcome. So it means that you at least require, as in convolutional neural networks, like a fully connected layer that's gonna, with some weights, grab your results and convert it into, for example, this regression task. So this is basically how it is done nowadays. So I mean, like the majority of architectures that are constructed, and those that I'm personally using, they are like those. But why still it's good to get not only complex numbers that have these rotations and like these stabilities with Fourier transform? Because in the quantum world, there is another stuff that is called entanglement. And this is this sign here, this dot with plus. It means entanglement. And basically, this is kind of if-else condition embedded into your neural network. So with quantum bits, you can have such a thing saying that regardless what's gonna happening, let's say with this bit, if this gonna become 1, finally this one gonna occur to be 0, for example, yeah. And I mean, this is really super exciting, because just imagine for a second how you would imitate if-else conditions in your classical neural network. I would say there are ways to do it, yeah, but they are super complicated. So there were a couple of researchers at NeurIPS even published, but they are all really like super complicated that I think nobody uses them now. But this part I would say that it's really useful, and this is, I would say, even the main reason why these quantum machine learning, quantum neural networks come into power. The good reason, for the question here, let's say if somebody raises his hand and asks me like how to train it, yeah. So because okay, cool, we have now, let's say, these classical parts. You are now guys saying that we have some quantum stuff here, again classical, but we usually make like a backpropagation. How would we backpropagate through this weird architecture that we have, like the mix of the classical and then some what you are calling like if-else entanglements? There is a way to do this. It's again, automatic differentiation comes to help, and those of you who are using PyTorch, you definitely should know about it. So because automatic differentiation was like the main idea behind the PyTorch when it appeared, and yeah, in quantum world, the library for Python, for those who are curious, is called PennyLane, and basically you see it appears in 2018, and since then it is widely used. And the good thing is that you can make a connection to PyTorch in order to then have all these architecture trained all together. And here is just, I mean, the gradient in the quantum is calculating like similarly, you know, like to the definition of the gradient that you have at university, I think on the very first lecture on the calculus. Yeah, and then later on you can just embed it into your network, into your classical network, and as I said, with PyTorch connector. Yeah. So I'm going to leave links for you here if you would be curious to find out more about it. So good. As I said, now we can train it. And again, coming back to like why we should it, because I told you, okay, there is this if-else condition, yes, super fancy stuff, but when it exactly makes sense, I can tell you when. So this was, let's say, you know, I was at one like event here. There was a guy who was trying to sell quantum machine learning, and he was telling about quantum support vector machines, quantum eigenvector solvers, whatever stuff. But the truth is that whatever machine learning method you are converting into the quantumized version, this might make sense because of, first, requiring, let's say, how to say that you might require finally less parameters, like less deep network in order to find out some complicated dependencies, basically because of these, let's say, either nature of the data set that you have, or the luck if you found the right if-else conditions, and then it means that basically your network becomes much shorter than the original one. And I mean, just understand me correctly, that natural data, naturally quantum data, it's not that often event that happens. So for example, here in Geneva, in CERN, they have a lot, obviously. So because it comes from this reactor, and there obviously the data is naturally quantum. That's why it's naturally encoded in the quantum, and it has these if-else conditions already inside. So our task is just to find exactly, you know, like with let's say hyperparameter search in the classical way. Yeah, we just need to find exactly the right architecture that's gonna catch almost immediately all these hidden connections that we have. And like with classical, we're gonna spend like huge deep architectures, and still we might not catch these dependencies. The other thing is if you have some complicated correlations, and basically, like, for example, there is, I mean, I told you only about like this usual stuff, yeah, that if-else condition. But in quantum, there is like additional thing that you can make, for example, if-else condition. So you can connect like two bits, and depending on their outcome, you can control the result of the third one. So this is even more powerful stuff. But as you can imagine, it's even more complicated to find this kind of dependency. And meanwhile, IBM has shown this advantage of finding complicated correlations with help of exactly like these super entanglements, but with the quantum SVMs, with quantum kernels on artificial data. So real data real constructed data, that like real task where you might need to get these complicated dependencies, it was not yet found. I think IBM spent like about 2 years for this research. They had like a separate group that was trying to, let's say, imitate these kind of things. And to the best of my knowledge, as of now, there is no success in it. But let's say if tomorrow somebody comes to you and asks like, what did you know from this lecture? Like, what is the real use of quantum machine learning? You can tell a lot of things that would be like half true and like half false. For example, like fraud detection. Yeah. So imagine, yeah, for example, that you can have like in parallel a lot of let's say patterns of behavior. Yeah. And since you're thinking immediately that there are a lot of potential, let's say, tracks, and you need to find the best one, then you can think about like, let's say, fraud detection. You can think about the optimization of logistics, etc., etc. So some things where you can exactly imagine following several tracks and better to understand like which of them have, let's say, like high probability for successful outcome. Other thing of, let's say, naturally quantum data is molecules. And since, because I mean, initially, like Dr. Attila asked me if I want to give this lecture, but the main reason why I also wanted to do this is because I know that for the computational biology, this might be really interesting. So, as of now, it's mainly used for computational chemistry because they're, let's say, the connections inside the molecules, they have this quantum nature. So basically, if you like ever heard of some, let's say, nuclear magnetic resonance or whatever, think in this direction, basically simulating the molecules using these ideas of entanglements and having, let's say, in parallel different options of how the molecule, of how the bonds could be constructed, and finally figure out, let's say, which of them would be the most plausible. This is the thing that people are already like doing, and here also in Switzerland. And later on, I'm gonna give you an example of how it is used. Yeah, but basically, I would say, like at this slide, how the possible applications are summarized. And one more application that was recently revealed, and I would say again, this is like the matter of discussion, is the quantum language model, large language model distillation. So you definitely know that now in LLMs, now the trend is to make it like with as like small number of parameters as possible without the loss of quality. And basically, there was a cool research. I'm leaving like the link here, how guys were able to distill LLM without, I guess, like with drop of 2-3% of quality, but with having much smaller number of parameters. And you understand as data scientists that much smaller number of parameters means being less prone to overfitting. So I would say this is kind of the main advantage of constructing these quantum circuits, that if you were able to find like this small quantum solution, it means that you would be like much less prone to overfitting. And this is a good thing. So I really recommend you to like listen to podcasts about it and to also look into paper. Yeah. Then couple more examples. So like, as I said, yeah, already like fraud detection, and then like I think Goldman Sachs used some financial instrumenting, like Moody's were using like in order to predict, like to simulate cyclones. But let's say these first 3 examples, they are not about quantum machine learning. They are about quantum simulation. So basically, these guys, they knew in advance some parameters, and what they tried to basically simulate all the possible outcomes at once and trying to understand like which of them would be most likely. So basically, because of this way of quantum simulation, it works much faster. But what I really consider to be like a good use case is Honda. So Honda, you might know, they have like pretty strong Honda Research Institute. And the good thing that they did, they made like the large image analysis because they have like very high resolution images, like about 2 million pixels. And if you think how you're gonna process it classically, so I mean like how we try to do it, yes, I think you can finally use some kind of attention-based approach, also like using convolutions there. but it's gonna be like very heavy solution. And I left for you the link because of the way how you can encode images with this quantum circuit. I can tell you that you need to have n quantum bits in order to encode 2 power n by 2 power n image. So basically, it means that when you are talking about like super high resolution images, this is like the golden thread. Really, this might help you a lot if you have access then to quantum computer where you can process this image analysis. But a lot of examples of why not yet, let's say everybody, why only Goldman Sachs and like Moody's and whoever Honda allowed themselves to do this kind of experiments. First of all, because it's like, let's start from the end. It's super pricey. So I would say that currently we are at this stage where only like let's say super big like research groups and maybe I don't know like institutions in Switzerland can allow themselves to burn money for this computation, because I can tell you that training, let's say one quantum neural network, not the most complicated, this might cost you like about several hundred thousands of Swiss franc, so basically euros. And I mean, like with just usual GPU, you can buy so many GPUs for this price, and like to burn them literally. Yeah, Attila, please.
So it would cost several hundred thousands of francs to train the whole thing, or just to train for a couple of epochs?
It's gonna, let's say, like from what I have seen, this is gonna like train up to convergence. It's gonna be like not for a couple of, just from my experience. So like when you are training, let's say,
a couple of seconds, or how long will it take?
So it's gonna take you finally like several hours. So it means that yeah.
Okay.
Yeah. So, but here I'm saying also obviously with the case of hyperparameter tuning, etc. So I mean, like this is not just a single training thing.
And why is it expensive?
It's expensive because just like 1 second of calculation costs $1.6. So like, I mean, the technology itself is just expensive.
As far as I heard, it's you need to cool this computer close to the absolute zero temperature.
Exactly. So
you makes it expensive.
Yeah, exactly. So the problem is, first of all, that in order to just organize, let's say, these ion traps, for example, the most expensive elements on the planet are used, like like palladium, gold, etc. So I mean, like if you ever seen like the pictures of the quantum computer, it shines like the golden throne. And the thing is that this is truly because gold is used there, and also like palladium and other metals. And you are absolutely right. The electricity that is required for cooling down, this is absolutely enormous. And also the other reason is that companies that have quantum computers, they have only almost monopoly. It's like oligopoly to some extent. So there are not that many computers, and that's why they can like put whatever arbitrary price on this kind of computation. Yeah. So like unfortunately, a lot of reasons for making like too costly, and yeah, yeah, exactly. So you really now have like many research groups around the world, and also like big companies that sorry, Roman, could you please mute yourself?
I think just the microphone was on.
Заебётся, я не хочу звонить секретарям.
Roman, sorry. We can hear that you don't want to call, but if you switch off your microphone, thanks. So basically, exactly, high demand, very limited amount of quantum computers, and the price of materials, and exactly like the cooling, etc. So this is like pretty huge.
Okay, thank you.
You are welcome. So I wish to gift you a quantum computer, but not yet. So, but as I said, that if you have powerful enough GPUs, basically you can try to simulate the process of up to 32 quantum bits, even on your laptop. So, but this is another question. But let's say the other thing why this is like so costly, because obviously, yeah, like introduce an additional quantum bit, it requires you like additional material, additional like microcontrollers that are trying to make sure that everything works. But the thing is that in order to have, let's say, this one, it's called logical quantum bit, yeah, that we're going to be using finally in our training, you need many physical quantum bits that are gonna be working in order to isolate these quantum bits from the outer influences. So the thing is that sometimes it's just the case that, for example, you want to create this entanglement between, like, let's say, quantum bit 1 and quantum bit 2, but because of like instability of the environment, this quantum bit 2 really wants to get entangled to environment, but not to this quantum bit 1, and this causes like so many problems, honestly. And yeah, later on we're gonna see like what are like the problems that come here along. But yeah, let's move on. So basically, as I said, you're gonna see a lot of lie on the internet now, and what you can trust. Basically, I would say that if you look, for example, here I provide like the latest news that were on quantum, at least I mean discussed in the quantum community. First of all, it was this CEO of NVIDIA who said that, you know, like quantum computing, it would like maybe in 30 years it would work. As of now, he sees like no opportunities. But I would say, you know, taking into account what happens now to NVIDIA, I would better recommend him to look after his company, yeah, but not into quantum. But then there was, you know, like a huge like piece of news with this Microsoft. Maybe you have even heard about it, that Microsoft released like the new Majorana computer, and they say that, first of all, these Majorana particles, this is just the new, let's say just the new type of particle, let's say just innovative material. Yeah, these Majorana particles, first of all, they are absolutely noise resistant. So it means that, as I said, yeah, in order to have like one logical qubit, meanwhile, you need a lot of helpers, yeah? They are claiming, first of all, that this one is going to be like absolutely clean without any kind of errors and noise, being noise prone. And the second one is that they are so easy then to be created, so that in like few years they're going to be able to create like quantum computer with already millions of quantum bits. So I can tell you that obviously this was like a big piece of news recently, but if you look, first of all, Microsoft was publishing papers about these Majorana particles for already 10 years, and every time there was a mistake there found. So I would say that I would wait for a little bit rather, but moreover, like let's say what they are claiming without any disclosure of like information and like more details, that now they have constructed it with 8 qubits. That the process itself was so like, let's say, expensive and like so complicated to establish these noise-prone quantum bits, that only quantum computer of 8 quantum bits they were able to like construct. That's why they would not share it with anybody else meanwhile, so because it's like so fragile. But later when they have bigger one, they would open it to the world. So I mean, really, I would not believe these things immediately. And, you know, also, for example, like this very recent piece of news, like from 3rd of March, that like some Chinese like processors, they like established like the new computer that is again like super stable, etc. You know, really better not to go deeper into this type of news. What I would recommend you maybe to look into, if you wish, are news about the software and algorithms, because this is the real thing that happens. This is like independent, like on the, let's say, these hardware properties. And if you really want to see, I would recommend these IBM Quantum research. So they are basically based here in Zurich, and they are providing a lot of stuff. So yeah, to these guys, I know that they are doing the real thing. And if you not really want to, let's say, read news, but you also want to try something out by yourself, by your hands, and I said like usual computer is also like available for smaller things. First of all, this PennyLane that I already announced today, this has challenges, and basically it looks like LeetCode or Code Wars, whatever. So it's like a platform where you can like just get registered, code, and run quantum computational tasks. The other thing that, I mean, for you as for data scientists, it might be interesting to go to Qiskit. So Qiskit is they are like competitors, PennyLane and Qiskit. PennyLane is provided by the Xanadu organization and Qiskit by IBM. So Qiskit has like a full machine learning tutorial, and there, like, I mean, since you're higher school of economics, you might be interested, in the option pricing with quantum GANs. So basically, like the possibility of creating exotic option pricing, or like doing some quantum Monte Carlo simulation, etc. So, and there is the other thing, for those of you who are still like considering himself being data scientist but doesn't like coding, there is like Quantum IBM Composer. So there you literally can create this circuit that I was showing to you without coding. So you can just create these connections, entanglements, rotations, and do it. The only problem is that currently the access from Russia is restricted. So you might like think how to, I don't know, like register for some of your friends who is in Europe. Just a little bit of shameless self-promotion. I was recently giving a talk about like differences between Qiskit and PennyLane, so please feel free to visit this link and find out more for those of you who want to program more. And now, finally coming to the stuff why I consider this might be interesting for you. So, because I mean, like I personally was doing with Dr. Attila my thesis about the mass spectrometry, I mean, there is like the adjacent thing that is, I already mentioned it today, the nuclear magnetic resonance. So I don't know, like if some of you work on it, but basically this is about the thing is that these nuclear magnetic resonance devices, they have like the quantum nature itself. So it relies on the quantum phenomena of quantum computations, and basically like it is providing like huge magnets that are then influencing. If you ever had, like these MRT, yeah, so you can go like into this huge tube, and there is like huge magnet around you, in fact, like flying around you, and basically what it does, it makes like your cells molecules inside, so basically they are little magnets, and what this magnet does is brings, let's say, like your internal magnets from their normal position into the one that they wish to be. So this huge magnet can force your internal magnets to stay in whatever position they like. And then when the magnet is turned off, your magnet is coming back to its normal position. But also coming back, it produces waves that are then registered, and based on exactly like what wave has been produced, we can guess what is in your cells. So we can exactly get like the chemical contents of your cells. And this is basically what we normally see. So because we rely on the H1 or C13, so the isotopes of the hydrogen or like the carbon, and basically then we can see such a picture. So this is called like NMR spectra. So this is like mass spectrometry, yeah, that you might know already, but this is NMR spectra. And the thing is that
spectrometry data a real one, or is it just for illustration?
Those are all real data sets. So like I also attached the link. So the thing is that maybe you have heard, like at NeurIPS last year, there was like a huge data set released on like the multimodal data set that has like NMR, IR, and MSMS data, and they are like coming to the same molecule. So like these are different spectrums that are corresponding to the same molecule, and basically like this is like a new data set that is now heavily explored in the community who is working on this multimodal approach to different like problem solution. And I think is
because
that
for this MSMS simulation, the simulation is very, very poor.
Absolutely. Yeah, but the thing is that
Yeah,
but yes, exactly, Attila. But for NMR, it is much better. So the thing is that simulation for NMR works much better. So the thing is that in order then to solve some problems that are using NMR spectra, and this is now what I'm personally like concentrated on, is that you like the major like machine learning methods are now processing just the NMR spectra itself, but as I said, originally, it comes in the form of wave. And basically, using this kind of the idea of quantum encoding, since the signal has quantum nature itself, you can in fact have like the encoding without the loss of precision. And like in these things, precision is very important, because since you are coming like to this kind of bin representation, you always need like to really take care about precision. Because like when we with Dr. Attila we were working on mass spectrometry, we really had like a huge difference, like working on precision of just, let's say, when we have 2,000 bins and then we have like 200,000 bins. So results were different, and you can imagine that the size of models were very different. But you wish to have as high precision as possible, obviously. So this is the thing, like that now the, let's say, quantum machine learning part that I'm working on, this is almost, let's say, like precision, like the solutions without loss of precision. This is like kind of the track that I'm trying to follow. And this one I leave for you as just a final note instead of conclusion. So in order to understand like that quantum AI, yeah, at some parts it is really cool, and it already we see that it works, but it is too expensive to use it for small tasks, because the uplift that we get, and you can see it like from papers that I have left on the slides. So let's say the accuracy uplift that we have and the price, how much it's gonna cost if we use this kind of solution, yeah, it's absolutely incomparable. So that's why now the majority would rather burn a couple of GPUs, but not to run quantum computer. And for like super huge tasks, we still lacking just qubits, and we just, let's say, now can either wait when more stable and bigger machines are released. For example, IBM is promising till the end of this year the computer with 1,000 qubits. Okay, let's wait. Or what, let's say, I'm personally more concentrated on is developing algorithms that just require less quantum bits. So you are coming up with better algorithms with smarter encoding architectures, where you can use like less qubits in order to, let's say, encode like huge data sets and then process it in quantum manner. Yeah. So that's why I still like there are a lot of tasks in these terms, but what is now, let's say, community working around is such a called quantum extreme learning machines. Maybe just usual extreme learning machines, but there is like the interesting variation of quantum extreme learning machines, where basically you have like the single layer, like your data, then single layer with hidden one, and then the outer layer is just the inverse matrix of your first multiplication. And there, since I said that quantum, so first of all, quantum, since we are normally doing rotations, this is very easily invertible. So comparing to just the normal, let's say, matrices that if you would like to invert in your just machine learning task, it's like a super complicated problem. With quantum ansatz, sorry, quantum circuit, it's very easy to invert. And the other thing is like quantum reservoir computing for machine learning. Maybe just reservoir computing. This is when you have like parts of your neural network just fixed. So basically, you are saying that this part we're going to fix and the other one we're going to train. And let's say this fixed part is going to be initially complicated. Some, I don't know, like a recurrent neural network architecture with some fixed parameters that should somehow better process our data. And then we're going to train like the rest, like simple linear, let's say, neural network. So since I say that quantum is more capable of making these like advanced encoding, basically people are now working on creating these kind of quantum reservoirs, yeah, which are not trained finally, but then you are training like the classical part with the linearity. So basically like this. Yeah. And yeah, just for more tips and tricks, you can find one of my lectures that I was given here, like in Zurich. And yeah, so I would say that's it, mainly. So I think we still can have like a couple of additional questions, except from, yes, look at quantum startups, see where you can work potentially. And if you are, for example, interested in career in Google and you want to move to California, I think now this is the best time, because Google has opened Google Quantum AI work group, and they are still heavily hiring people. So maybe it's not too late if you like learn quantum today and tomorrow apply to Google. So this is in Santa Barbara. So those of you who are watching this TV series, so you might know it. Okay, cool. So then just keep calm and work on quantum AI. And I think that's it from my side. So please, questions are welcome.
Thank you, Paul, for this interesting talk. My first
you.
questions: are you applying to Google?
The problem is that I love Switzerland. So yeah, and this Google Quantum is only in US. Yeah.
You probably would like or love California too. It's not
Too-
United
oh,
States.
Okay, thanks. I will think about it.
They have a better climate. They have
really?
no snow, absolute.
All right, thanks. That's really cool.
Okay. So is there from the audience, I'm asking the audience, has anybody got some questions? Sengmin, probably you should have some.
No, it's thank you. So the interesting part. So I got very small amount of qubit from IBM. So I was trying to understand how to programming this qubit QSIP. I don't know. I don't remember exactly. But so in the beginning of this years, I tried to actually predict the like a rotary. But based on your explanation, why I failed to predict the rotary, so I think that's so I thought it's like a quantum might have some kinds of solution may find which is very expensive, but it seems like it's not working like that. So it's so in your based on your explanation, so it's like it's more close to the like a parallel computing with a huge amount of GPU can replace by this quantum computing, but right now it's too expensive to replace it. That's why it's what it is or something.
So I would say more the think about, let's say, parallel computing. This more relates just to quantum simulation advantage, not the advantage of the machine learning itself. So with machine learning, I would more say that it is about entanglements. So this power of entanglements, power of just like, as I said, like a single control bit and then like the other dependent, or like two control bits based on which you just make a decision. I would say this is more important because this exactly gives you possibility to find like the right correlations in your data with without a need for deeper architectures. But this parallel computation, this is cool, for example, for things like there is quantum Monte Carlo simulation. So you might have heard about it. For example, if you look at this link from Moody's and go deeper, you would see that it's cool when you have, or for example, okay, let's now go to like things like weather, but let's say poker. Yeah, there are lovers who enjoy quantum poker. There is such a thing. So you have like so many possibilities of the cards from the deck at the same time that people really think that they can in parallel, like based on like the other coming cards, to simulate what are the opportunities and like immediately get the decision. But this is obviously like not working. Yeah, so this is all just just stupid stuff. So yeah, simulating in parallel, this is the stuff, for example, the very first, I would say, example was the best one in terms of like parallelization, this one, so Shor's algorithm. So this is a perfect example of how this done in parallel, but this is like, for that we need to know a little bit more about quantum Fourier transform. The other thing that I would recommend, I can write it in chat, so I really recommend you to look into this. It is called Grover's algorithm. So if you didn't hear about it yet, so it is Grover's algorithm. And this is exactly the idea of how you can make, let's say, this parallel unstructured search. This is kind of a cool stuff, and because I would say Grover's algorithm is more clear in terms of showing the amplifications of probabilities. So just in these terms, I would recommend to go somewhere in this direction. But in terms of machine learning, no, I would say it's more about these things like entanglements.
Okay, thank you.
Yeah, you're welcome.
Other questions?
Yes. Hello. Yeah, thanks for the talk. Well, to be honest, I didn't get maybe 50% of it because it's quite complicated from the
No problem.
Yeah, because I don't have basics, but well, I remember your PhD. I think it was a little bit different, but still, and now I get that you kind of enthusiastic in this field, but well, how from your point of view, how is it really? Well, let's formulate. So, up to what scale is it really applicable and like perspective for the real task? Because your example about IBM, a group who was like searching for the interesting and complicated examples and didn't find them for 2 years, it's kind of demotivating. So is it like the just kind of interesting mathematical area where people can like play scientific games, or is it really a deal? I mean, this quantum machine learning. So is it a real competitor for let's say modern large models like transformers and etc.?
Yeah, good question. So I would say that my main thoughts are two. So first of all, since we get like, let's say, more powerful and cheaper quantum computers, for example, this task of LLM distillation, this is going to become pretty important. So because imagine that really you can shrink significantly the like amount of parameters that you have, like, and the depthness of your solution, and basically have kind of the same output quality. So just as I said, yeah, basically we are not yet at the point where it is economically like efficient. Yeah. So here, and the other thing is about already these applications where you have, let's say, some quantumly natural data. Yeah. And for example, at this particular case, you do not need to require like a huge amount of quantum bits. So waves, they could be really easily encoded with the small number of qubits, but definitely you can have like better like encoding and then like a faster solution because really you would immediately, like on the very first couple of steps of these rotations and entanglements, you would already catch the dependencies of your data, and then you can, for example, proceed with the classical way if you don't want to train like a huge quantum circuit. Yeah. So that's why it's about like data that fits naturally, or either fits naturally as an input or fits naturally as an output. For example, if we are talking about about the molecules. And the other thing is, and this part is called like quantum chemistry. If you are interested, like here, for example, PennyLane, you can go to challenges and see the quantum chemistry. So you can click, there is like the part that is called quantum chemistry. I really recommend you to study it. Yeah, and the other thing, as I said, like this economical stuff with for example, LLMs distillation, kind of.
Okay, yes, thanks. And yeah, maybe very brief question. So latest advantages in LLM, like I'm asking about this area because I'm mostly familiar with this. So what many latest advantages in LLM performance, etc., they're related with the let's say programmatic improvements like flash attention. So some tricks that help to increase the computational speed and so to make models larger and more effective. So they're not theoretical and they are. So when you're talking, you mentioned some applications, and mostly for all of them, you wrote that something like that it helps to decrease the costs, the computational costs. So maybe it's like so how to my question actually is how to measure how honestly measure the cost, because we have two parts actually: the theoretical computational costs, so algorithmic complexity, and real computational cost on the on the like on the real in the real industrial tasks in the real on the real machines. So and it can actually it can differ because it depends on what kind of tricks you are using directly on machines. So what can you say here about that? So do this community have something similar to this? So do they try to make some improvements based on the apparatus level or not?
I can tell you that now in the majority of quantum machine learning papers that you're gonna find, they have this kind of thing of measuring like the complexity, not the complexity, but they are, let's say, introducing different number of qubits and different architectures, and then making a benchmarking regarding, first of all, how fast this architecture is trained up to convergence, and obviously what kind of accuracy you get on your test set, on validation even during training. So these, I would say, like two main benefits where you can directly compare to the classical, because this is very important, that I bet you understand it, that quantum bit doesn't equal to neuron. It's not one-to-one comparison, and this is now the main problem. That and again, I really recommend that if you're gonna read some quantum machine learning papers, some people confuse it. And they say, look, my neural network has like, 3,000, neurons. And this one has only, like 100 quantum bits. That's it. Yeah, I win. No. So the thing is that if you look at the time that it took to converge this kind of stuff, let's say, and the accuracy, it might occur that it's far away, not like this. So I would say, these are two main things that you like measure the real things, like the time for training, time for convergence, and also accuracy, and you are basically evaluating both like classical architectures and their complexity and the complexity of quantum. This is, as of now, this is the only way how to compare them and to take advantage, to see if you have finally advantage or not.
Okay, thank you. Yes, I get it.
Okay, you're welcome.
Okay, so now I have questions. So I have 8 qubit in IBM. So how does it, this 8 qubit might be equal to the GPU?
Equal to GPU? I'm not sure that we can compare.
In terms of for example, you said about accuracy. So in terms of accuracy and convergence of these models. So let's say that we have a same. So I have a transform model in the which is trained by the GPU. But let's say I want to transform. So I have this resource. I want to do some toy project to understand how this works. So imagine that I have some transform model, some encoding some physics, so some kinds of the gym environment, and then I want to understand that this physics environment. So usual approach is like a partial differentiation or the ODE. It's very expensive computation required to understand this physics. But instead, let's say I want to use this. I will convert this code for GPU design to targeting the GPU code into this Qiskit. Yes, Qiskit, right? Is it? So Qiskit code. So, but I have a very limited amount of the qubit, like 8 only. So, do you think it's worthwhile? Is this worth to try to compare this to like in GPU in terms of this quantum unit?
I mean, it makes sense to compare it in terms of, let's say, as I said, like these training time and accuracies. But let's say in terms of like how, because as I said, maybe I need to clarify it, that if you do not have a real quantum computer, there are mathematical rules for simulating the behavior of the quantum bits, and also entanglements, etc. And the thing is that in order to do these kind of things, you can just run on this Qiskit, for example, you can call simulator. You do not need to connect to IBM machine that stays somewhere in Toronto, yeah, but you can just make your own simulation. And then you can, for example, see if you are talking about GPU, yeah, you can, for example, take these 8 qubits, you can run simulator and see how much of the GPU was used, for example, by these 8 qubits. You can just monitor, you can literally see like how much it was, and then see like how much GPU was used by your transformer. And if, I don't know, the accuracy is comparable, you can just say like, okay, these 8 qubits, they used, I don't know, twice less GPU resources. Cool, I'm gonna use them, for example, yeah. So, but truly, like these are the only like comparables that you can make.
So then, what's the main benefit I can get from using the instead of GPU to? So if I have a transform to my code, transformer code into the like a Qiskit in the quantum unit, what's the main advantage it would be like in terms of like simulating the physics in the environment?
Okay, in terms of simulating physics environment, so okay, if we are now talking exactly about simulating physics environment, this goes more into the quantum simulation of quantum machine learning, and this is about, as I said, the complexity of algorithms. For example, if you would talk about NMR, yeah, there is like the if we go, sorry, here. So for example, in NMR, there is like like the task of, for example, coming from molecule back to spectra. Yeah, so you can take molecule, you can create a spin system, and you can go back to the NMR spectra. And this is pretty, let's say, well-known task. There are a lot of methods, classical methods, how it is done, but it mostly relies on the computation of Hamiltonian. So you definitely need just to find the right parameters of the Hamiltonian of the system. Yeah, and for example, like how it is done now, yes, so you just using some algorithms for that. But if you replace, let's say, this Hamiltonian with the quantum circuit, yeah, so you can do this. So basically, you would have not just a single Hamiltonian, but you would have like several qubits, yeah, that gonna be trying to simulate kind of the same final result of this Hamiltonian. You just can basically see, first of all, how fast you get it, yeah. You can see exactly, let's say, how many peaks you finally like detect with this or that method, yeah, and etc. etc. So I mean, the measurement, yeah, the measurement is up to you. It's exactly like your trade-off. If you are a huge company, you are mostly interested in money. Yeah. If you are like the single researcher, most likely you are looking at the accuracy that you get. And like, I mean, if Dr. Attila provided for you access to GPUs from HSE, yeah, then most likely you don't really care about how much GPU you're gonna burn. Yeah. At least this is how it was for me. Yeah. We didn't really care like about GPU, because at some point we just got a computer and it was staying like in Attila's office. So, but obviously, like really, it depends like what is your measure of success. Yeah. So this kind of the stuff.
Okay, thank you.
You're welcome.
Other questions?
I had one. Am I audible?
Yeah,
Okay.
please.
Yeah. So, when are we expecting that these quantum computers would be comparatively cheaper? And with the growth of the machine learning and the classic ML, would we be expecting that the comparison would be similar, or like the quantum computers would be winning the race in this case? Because we are seeing a huge level of advancement in both the fields. Though in quantum computers it's a bit slow, and in the classic ML it's fast. But with over time, are we expecting that there would be a drastic difference or not?
So I would say that, first of all, it's a very interesting question, because you might have seen that now in the world of AI, it's more like the trend for reducing like the complexities of architectures. Yeah. So like exactly like getting like less parameters, the same accuracy, etc., etc. And quantum is in fact targeting the same kind of idea. Yeah, from what I was telling. So basically, I think that the simpler classical architecture becomes quantums, then let's say it's less interesting to make quantum classical architectures. Yeah. So because let's say the architecture is already so much straightforward, so that to replace some parts with quantum makes no sense. Yeah. But there are, let's say, still architectures that are in transformers that you would either way need to somehow, let's say, simulate, and you cannot get rid of complexity some particular parts. So there, I think that quantum can still win. Talking about the time horizon, when it's going to happen, really hard to say, because here this Moore's law, I'm not sure it works. So because like this about transistors, etc., and since now quantum computers, they are definitely not about transistors. So I would say, like, from how the community develops and from how much money I see being invested into it, yeah, this could be two ways. Either we're gonna be really like witnessing something cool, I don't know, like in 5 years, since like looking to what Google and IBM are promising, or it's gonna stay the same as thermonuclear physics. It's always, if you look at news about like thermonuclear reactor, it's always 30 years till when we get a thermonuclear reactor with like thermonuclear energy. Yeah. So basically, I think really. So meanwhile, it's hard to like predict, but I'm pretty sure that in 5 years we definitely would get the answer, because if we're gonna see that there was exactly the progress made that was expected, then it means that let's say 5 more years after that, and we're gonna have already like absolutely noiseless, super cool quantum computer with thousands of qubits. Let's say, yeah. If we don't see it, then it's the same like bubble as the thermonuclear energy. Yeah.
So for now, as a young generation person, should I be upgrading my skills towards the quantum ML or the classic one?
I would say that definitely it would be not, let's say, the bad hobby, yeah, to look into the quantum ML, because, like, again, to the best of my understanding, either way, this would have a lot of niches, So even finally, if, for example, I don't know, it would occur that transformers are not beatable, but only, for example, it's like the architecture reduction, I still think that, for example, cases like quantum reinforcement learning, this is still very like not that much described topic, yeah. And there is like let's say, coming back to the questions when we were talking about the parallelism, yeah. So imagine that you can explore several strategies of your agent in parallel, yeah, and exactly then evaluate the probabilities of those strategies that leads to the better outcome, and to train it not like in a classical way, but through the fast, let's say, backpropagation in several iterations up to cool convergence. So I think that really, if talking about general quantum ML, yeah, I would say that it would be never like a comparison that quantum won over classical, but at some niches, I would say yes. So, and like the niche of the data, yeah, that you find like really like the data that now I'm showing, for example, NMR, or like, for example, what we were recently doing is the data on galaxies. So, for example, if you take like the signals that are coming from galaxies, the waves that are coming from galaxies, they also have like the quantum nature inside, and they are very naturally encoded into the quantum circuits, yeah. So that, for example, like data, or like this idea about, I don't know, like quantum RL, though myself, I was not investigating this too much, so that's why if you do it, I would be very interested to discuss it with you, yeah. So that then maybe find out something like this. So yeah, I would say more like this.
Okay, thanks for the info. Really helpful.
Yeah, you're welcome.